Imagine if I told you that an object can exist in two places at the same time, that simply watching something can change what it does, and that nature itself refuses to give clear answers. Most of us would say that sounds impossible or even wrong. Yet this is not science fiction, it is quantum mechanics, the most accurate theory we have ever created. The problem is not that quantum mechanics is broken. The problem is that our intuition is. And that is exactly why Richard Feynman's way of explaining it matters. Quantum mechanics is confusing because it completely defies the way humans naturally understand the world. From the moment we are born, our brains learn how reality works by observing everyday objects. When you throw a ball, it follows a clear path. When you push something, it moves in a predictable way. Cause leads to effect, and objects exist in one place at one time. This way of thinking works perfectly for daily life, but it fails when we look at the universe on the smallest scales. Quantum mechanics describes the behavior of atoms and subatomic particles, and at that level, the rules change so dramatically that our intuition becomes unreliable. One reason quantum mechanics feels so confusing is that particles do not behave like solid objects. Instead, they act like waves, spreading out over space rather than following a single path. An electron, for example, does not orbit the nucleus like a planet around the sun. Instead, it exists as a cloud of probabilities, meaning we can only calculate where it is likely to be found. This idea clashes with our instinct to imagine objects as having clear positions and boundaries. Our minds want certainty, but quantum mechanics only offers probabilities. Another source of confusion is the concept of superposition. In everyday life, something is either on or off, moving or still. In quantum mechanics, however, particles can exist in multiple states at the same time. An electron can spin both up and down simultaneously, and a particle can travel through multiple paths at once. This is not just a theoretical idea, it has been confirmed through experiments. Yet imagining something being in more than one state at the same time feels impossible, because nothing in our daily experience prepares us for it. Measurement adds another layer of difficulty. In the classical world, observing something does not change it in any significant way. Watching a car drive by does not affect its motion. In quantum mechanics, measurement fundamentally alters the system being observed. When scientists measure a quantum particle, its wave-like behavior suddenly collapses into a single outcome. This means the act of observation plays an active role in shaping reality, which feels deeply unsettling. It challenges the assumption that the universe exists independently of our attempts to measure it. Quantum mechanics is also confusing because its mathematics is far removed from everyday language. The theory relies on complex equations, abstract symbols, and higher-level mathematics that most people never encounter. Without these tools, explanations can seem vague or mystical. Many popular descriptions oversimplify the science, while technical explanations feel inaccessible. This gap between the math and intuitive understanding makes quantum mechanics feel mysterious rather than logical, even though it is one of the most precisely tested theories in science. Another reason quantum mechanics feels so strange is that it contradicts common ideas about cause and effect. At the quantum level, events can occur without a clear cause, governed only by probability. A particle can suddenly appear in a new location without traveling through the space in between, a phenomenon known as quantum tunneling. While this behavior is normal for particles, it violates everything we expect from physical objects. Our minds are uncomfortable with randomness at such a fundamental level. Finally, quantum mechanics feels confusing because it reveals that reality itself is not as solid or definite as we assume. Instead of a universe made of fixed objects following clear rules, quantum mechanics shows a world built on uncertainty, chance, and mathematical relationships. This forces us to rethink what it means to know something and what it means for something to exist. The discomfort comes not from a lack of intelligence, but from the fact that quantum mechanics asks us to abandon deeply ingrained ways of thinking. It is not just a new set of facts, but a challenge to human intuition itself. Richard Feynman believed that true understanding in physics had nothing to do with sounding intelligent or memorizing complex equations, but everything to do with being able to explain an idea clearly and simply. He often argued that if a person could not describe a concept in plain language, then they did not truly understand it. This belief shaped the way he approached quantum mechanics, a subject famous for confusing even advanced students. Instead of hiding behind technical jargon, Feynman tried to strip ideas down to their core, exposing what was actually happening beneath the mathematics. For him, simplicity was not a shortcut, it was the ultimate test of understanding. Feynman recognized that equations alone can create an illusion of knowledge. A student might learn how to manipulate symbols and arrive at correct answers without having any intuitive sense of what those symbols represent. Feynman found this dangerous, especially in a field as strange as quantum mechanics. He believed that mathematics should serve understanding, not replace it. When teaching, he would challenge students to explain a concept out loud in everyday terms because speaking forces clarity. If the explanation fell apart, it revealed gaps in understanding that equations could easily hide. This philosophy was especially important in quantum mechanics, where many concepts resist intuition. Instead of pretending the ideas made sense in a classical way, Feynman encouraged honest explanations that admitted confusion, while still remaining clear. He did not try to make quantum mechanics sound normal, he tried to make it understandable on its own terms. By avoiding vague or mystical language, he showed that clarity does not mean simplicity of reality, but simplicity of explanation. This approach helped students accept the strangeness of quantum mechanics without feeling lost. Feynman's teaching style reflected this belief in simplicity. He used analogies, stories, and concrete examples drawn from everyday life, even when discussing abstract topics. While he knew analogies were imperfect, he saw them as bridges between the familiar world and the quantum one. These explanations gave students something to hold on to, allowing them to build understanding step by step. Rather than overwhelming learners with formalism, Feynman focused on the underlying ideas that the math was describing. One of Feynman's most famous habits was his insistence on deriving known results from scratch. He would take established theories and explain them as if they were being discovered for the first time. This forced him to confront every assumption and ensure that each step made sense. If he could not explain a step clearly, he considered the understanding incomplete. This method prevented blind acceptance of authority and encouraged deep, independent thinking. It also demonstrated his belief that understanding is an active process, not a passive one. Feynman's approach also emphasized learning through teaching. He believed that explaining a concept to others was one of the most effective ways to test and deepen one's understanding. When you teach, you cannot rely on memorized phrases or formulas. You must adapt your explanation to your audience. This process exposes weaknesses in your own knowledge. Feynman used teaching not just to communicate ideas, but to refine his own understanding of physics. Ultimately, Feynman's belief in simple explanation was about honesty. He refused to pretend that confusion was the same as depth or that obscurity meant sophistication. In his view, unclear explanations were often signs of unclear thinking. By demanding simplicity, Feynman raised the standard for what it meant to understand quantum mechanics. He showed that even the most complex ideas can be explained clearly, not by removing their complexity, but by confronting it directly and refusing to hide behind complicated language. One of Richard Feynman's most influential contributions to physics was the creation of what are now called Feynman diagrams, which transformed how scientists understand and calculate interactions between quantum particles. Before these diagrams existed, calculations in quantum electrodynamics were extremely long, complex, and difficult to interpret. Physicists often worked through pages of dense mathematics without a clear picture of what was physically happening. This made the theory not only hard to use, but also hard to truly understand. Feynman realized that much of this complexity could be reduced if physicists could visualize particle interactions rather than only describe them through equations. Feynman diagrams represent particles as simple lines and their interactions as points where the lines meet. For example, an electron might be drawn as a straight line, a photon as a wavy line, and their interaction as a vertex where the two connect. Each part of the diagram corresponds directly to a mathematical term, but instead of starting with equations, physicists can begin with a picture. This shift was revolutionary because it allowed scientists to think visually about processes that happen at scales far beyond human perception. What once seemed abstract and chaotic became structured and understandable. The power of Feynman diagrams lies in their ability to simplify without distorting the physics. Rather than removing complexity, they organize it. A single diagram can summarize an interaction that would otherwise take multiple equations to describe. By breaking complex processes into smaller, visual steps, physicists can more easily see which interactions matter most and which can be ignored. This made calculations faster, more intuitive, and far less prone to error. As a result, problems that were once nearly impossible to solve became manageable. Another important aspect of Feynman diagrams is that they changed how physicists think. not just how they calculate. Instead of viewing particle interactions as mysterious mathematical events, scientists could imagine particles exchanging energy and momentum in specific ways. This mental picture helped bridge the gap between abstract theory and physical intuition. Even though the diagrams are not literal pictures of reality, they provide a conceptual framework that aligns closely with how the math behaves. This made quantum mechanics feel less like a collection of rules and more like a coherent description of nature. Feynman diagrams also made quantum mechanics more accessible to students and researchers alike. Learning quantum field theory used to require mastering advanced mathematics before gaining any intuition. With diagrams, learners could grasp the basic ideas early on and then gradually connect them to the formal equation. This approach reflected Feynman's belief that understanding should come before technical mastery. The diagrams became teaching tools as much as research tools, helping generations of students build confidence in a subject often considered intimidating. Beyond education, Feynman diagrams played a crucial role in advancing modern physics. They allowed physicists to make incredibly accurate predictions about particle behavior, many of which were later confirmed by experiments. The precision of quantum electrodynamics, made practical through these diagrams, is still considered one of the greatest achievements in science. The fact that such accuracy emerged from such simple drawings highlights the brilliance of Feynman's insight. He showed that clarity and power are not opposites, but partners. Ultimately, Feynman diagrams represent more than a technical tool, they embody a philosophy of understanding. They show that even the most complex phenomena can be approached through clear, visual thinking. By turning overwhelming mathematics into understandable pictures, Feynman helped physicists see quantum interactions in a new way. This ability to reveal order within apparent chaos is why Feynman diagrams remain central to physics today, and why they perfectly capture Feynman's belief that real understanding begins when ideas become clear. One of Richard Feynman's most important lessons about quantum mechanics was that true understanding comes not from trying to make it feel comfortable, but from accepting that it is fundamentally strange. Many people approach quantum mechanics hoping it can be explained in ways that fit everyday logic, but Feynman argued that this expectation itself is the main obstacle to learning. At the quantum level, nature does not follow the rules that govern common experience, and trying to force those rules onto it only leads to confusion. Instead of resisting the weirdness, Feynman encouraged students and scientists to face it honestly and learn how the universe actually behaves, not how we wish it behaved. Feynman believed that confusion often comes from demanding answers to questions that quantum mechanics does not allow. People ask which path a particle really takes or what an electron is actually doing when it is not being observed. Feynman pointed out that these questions assume a classical reality that simply does not exist at the quantum level. Quantum mechanics does not describe hidden certainties behind the scenes. It describes probabilities and outcomes. Accepting this does not mean giving up on understanding, but redefining what understanding means in this context. Rather than inventing comforting interpretations, Feynman focused on what the theory successfully predicts. Quantum mechanics works extraordinarily well, producing results that match experiments with incredible precision. Feynman argued that this success matters more than whether the theory feels intuitive. Nature is not required to match human expectations, and demanding that it do so only creates frustration. By accepting the theory on its own terms, learners can focus on how to use it correctly instead of being paralyzed by its strangeness. This acceptance also frees students from the false belief that confusion equals failure. Feynman openly admitted that quantum mechanics does not make sense in the traditional way, even to experts. Instead of hiding this fact, he treated it as a starting point for honest inquiry. When students realize that confusion is normal, they become more willing to engage with difficult ideas. Feynman's approach removed the pressure to pretend understanding and replaced it with curiosity and humility. Feynman also warned against oversimplified explanations that try to eliminate quantum weirdness entirely. Popular descriptions often reduce quantum mechanics to metaphors that feel familiar but distort the science. Feynman believed this was dangerous because it creates false confidence rather than real comprehension. Accepting weirdness means allowing concepts like superposition uncertainty and wave-particle duality to exist without forcing them into classical categories. These ideas are not metaphors, they are descriptions of how nature behaves. By embracing quantum strangeness, Feynman showed that understanding does not require visualizing reality in everyday terms. Instead, it requires learning the rules that govern the quantum world and applying them consistently. This shift is difficult because it asks learners to let go of deeply ingrained assumptions. However, once those assumptions are released, quantum mechanics becomes less confusing, not because it becomes familiar, but because it becomes internally coherent. The theory may still feel strange, but it no longer feels contradictory. Feynman's acceptance of weirdness also influenced how he approached problem solving. Rather than questioning why quantum mechanics works, he focused on how it works. He treated the theory as a reliable tool, not a philosophical puzzle that needed to be resolved before use. This practical mindset allowed him to make groundbreaking contributions, while others were still debating interpretations. Feynman demonstrated that understanding can be functional even when it is not intuitive. Ultimately, Feynman taught that embracing quantum weirdness is not a sign of intellectual defeat, but of intellectual maturity. It requires admitting that human intuition is limited, and that nature does not owe us simplicity. By letting go of the need for classical explanations, learners can engage more deeply with quantum mechanics and appreciate its power. The strange behavior of particles is not a flaw in the theory, it is a reflection of reality itself. Through this acceptance, quantum mechanics stops being an unsolvable mystery and becomes a fascinating, if still unsettling, window into how the universe truly works.